This is a video from section 12.3 and it's based off the lecture notes. Suppose we are given the equation of the line ax plus by plus c equals 0. And if you notice how this line is written, 0 is on one side of the equation and ax plus by plus c is on the other side. That's going to be important. Okay. Suppose x sub 1, y sub 1 is a point not on the line, and we want to find the distance from x sub 1, y sub 1 to the line ax plus by plus c equals 0. And don't worry, I will draw a picture of what's going on here. Okay. Now, let x sub naught, y sub naught be a specific point on the line. And what we want to do is we want to form the vector x sub 1 minus x sub naught, y sub 1 minus y sub naught. So you can think about it this way. Here's the point x1, y1. And the vector I'm referring to is right here. So this is vector v. Now, here's the claim. The claim is n, which is equal to the vector AB, is perpendicular to the line ax plus by plus c equals 0. And if you notice, I'm forming n by the coefficients of x and y respectively. Now, I want to give you an idea of why that vector is perpendicular to the line. Now, remember that x naught, y naught is a specific point on the line. And what I did was I chose a point xy, which is more arbitrary or general. It's a point that's different than x naught, y naught. And what I want to do is I want to look at the vector w, which is equal to x minus x naught, y minus y naught. And then from there, I want to show that vector n is perpendicular to vector w. And to do that, I have to show that the dot product of n and w is equal to 0. And if I can show that n and w are perpendicular, and remember that xy is an arbitrary point that's different than x naught, y naught. And so that's going to show that n is perpendicular to the line because we proved it was perpendicular to the vector, w specifically. Okay? I hope that makes sense. But we can definitely show this. This is not hard to show. Now, let's take a look at a picture here, another picture. So we have the line ax plus by plus c equals 0. We have a point x1, y1 that's not on the line. Now, when I say that I want to find the distance from x1, y1 to the line, I want the perpendicular distance down, right? So in other words, I want the distance from the point to the line straight down. So this has to be perpendicular. Now, again, I'm going to pick a point on the line and call it x naught, y naught. And I'm going to form the vector v, which is equal to x1 minus x naught, y1 minus y naught. Now, remember what I said. N is perpendicular to the line. Okay? So we need that. And remember that n is the vector AB. Okay? To find the distance from the point x1, y1 to the line, I'm going to take the scalar projection of v onto n. Okay? So, again, I want the scalar projection of v onto n. Now remember, I don't know if the scalar projection will be positive or negative. And so to ensure that I'm getting the distance, I have to take the absolute value of that result. And that's what I'm going to do on the next page. So the distance from D, the distance D from the point x1, y1 to the line ax plus by plus c equals 0 can be found as follows. So D is the absolute value of the scalar projection of V onto N. But that's equal to the absolute value of the dot product of V and N divided by the magnitude of N. Now, let's remind ourselves, V is the vector x1 minus x naught, and then y1 minus y naught, and then N is the vector AB, like this. So when I take the dot product, I get the absolute value of A times x1 minus x naught plus B times y1 minus y naught divided by the square root of a squared plus b squared. Remember, the square root of a squared plus b squared is the magnitude of N. So this is equal to ax1 minus ax naught plus by1 minus by naught in absolute value divided by the square root of a squared plus b squared. Now remember, the point x naught y naught is a solution to the equation ax plus by plus c equals 0. But what does that mean? If I replace x with x naught and y with y naught, it works. And that's what I did here. So we know that ax naught plus by naught plus c equals 0. And if I solve for c, I get negative ax naught minus by naught. So D is the absolute value of ax1 minus ax naught plus by1 minus by naught divided by the square root of a squared plus b squared. Now remember, if I take negative ax naught and I subtract by naught, that's equal to c. So on the next line, I get the absolute value of ax1 plus by1 plus c divided by the square root of a squared plus b squared. And so we got a formula to find the distance from a point to a line. So capital D is the absolute value of ax1 plus by1 plus c divided by the square root of a squared plus b squared. And then let's take a look at an example. So suppose I want to find the distance from the point 2, 3 to the line 4x plus 3y equals 6. But remember, that line is not set to 0, and we need to make sure that it's set to 0 or your distance will be thrown off, right? So 4x plus 3y equals 6. If I subtract 6 on both sides, you notice 4x plus 3y minus 6 equals 0. And so C is equal to negative 6. A is 4 and B is 3. And you already can see that I labeled x1 and y1. And so all I have to do is plug in that information. I'm going to replace A with 4, x1 with 2, b with 3, y1 with 3, and c with negative 6. And that's exactly what I did. So D is the absolute value of 4 times 2 plus 3 times 3 minus 6 divided by the square root of 4 squared plus 3 squared. And you will find that the distance is 11/5. And what's really fascinating, the equation of a plane and when I'm talking about a plane, think of a sheet of paper that extends forever in all directions. So the equation of a plane can be written in the form ax plus by plus cz plus d equals 0. Now, remember, just like with a line, it turns out that the vector ABC, which I'm going to call n, is perpendicular to the plane. Furthermore, now let x1, y1, z1 be a point that is not on the plane. So we have something that looks like this. We have a plane. So I'll just draw it this way. And we have a vector n. And we have a point that's not on the plane. That I'm going to call that x1, y1, z1. Okay? It turns out the distance d from x1, y1, z1 to the plane ax plus by plus cz plus d equals 0 can be found as follows. D is going to be the absolute value of ax1 plus by1 plus cz1 plus little d divided by the magnitude of n, which ends up being the square root of a squared plus b squared plus c squared. So you can kind of see it's a very similar formula to what we did earlier when we found the equation we found the distance from a point to a line, and it's a very similar formula. But we're going to learn about this formula that I'm checkmarking in section 12.5. But I would prove this result in a very similar way that I proved the earlier result. And that'll conclude this video for section 12.3, and this was a video based off the lecture notes. And this was all about distance from a point to a line. Thank you.